that is an incomparable step higher level of power from what you first started doing.
Welcome to the LabVIEW experiment. I am your host, Sam Taggart from SAS Workshops. In my 15 years of working with and training developers, I've had the opportunity to conduct a lot of experiments. Over here, we believe in embracing failure as the essential learning experience that it is. And what better way to learn than from other people's mistakes? In this podcast, I talk to industry experts, colleagues, and friends about their failures and how they have turned them into future successes. I am here today with Ben Leedom, who formerly worked at NI. And Ben is probably most well known. The reason I know him and the reason I met him to begin with was a presentation he gave at GDevCon in Europe, right? It was in Europe. Mm-hmm. And was it the first one or the second one? I don't remember.
I think it was the second one.
The second one.
2019.
Okay, that sounds about right. Yeah, so he gave a presentation on something called Rebar, which is basically, I want to say it's an implementation of Rust in LabVIEW, but that's probably not quite accurate. Why don't you tell us a little bit more about what it is?
Sure. I mean, that's pretty close. The idea was to take, sort of the theoretical ideas behind Rust, so Rust is this language that, kind of came out of Mozilla, was kind of, entered in the systems programming space. And the idea was that it had, these concepts of memory safety built into its type system. So it would check things like, are you using, references and pointers to things at times when it's safe to do so? Are you using references that let you change things or just read from things in a way that's safe? And so this gives you, not just checks on whether things are still valid at the time that you're using them, but also are you doing things concurrently in a way that's safe and so forth. And so I thought, if you look at these rules, the rules that the language applies, there are rules about what things are allowed sort of in time and what things are allowed to be ordered with respect to each other. And that's kind of a lot like LabVIEW, because LabVIEW, its syntax, it is data flow, but it is data flow that sort of structures things in a way that, orders things by, what has to happen before or after something else, not just how do you lay statements out in a list in a program. It's okay, does this thing use something from this other thing? Okay, well then they have to be ordered with respect to each other, and otherwise not. And so rules okay, if you have a reference to something, it must only be used after the thing is created and before it is destroyed. Well, that's a similar kind of sort of ordering statement that you could maybe potentially express in data books. So what I did was say, well, we have LabVIEW NXG. It's this fancy IDE that lets you plug in and create your own sort of definition of data flow diagrams and give them execution semantics. So it's okay, let me try this. I'll see if I can come up with something that kind of makes sense with the rules of Rust and the rules of data flow, and see how far it can take me. And I got, I'd say, kind of far. I got sort of the basics of the language nailed down. So it's you could define objects that had a lifetime, and you could create references to them, and it would check are you using all of those things in the proper way. And it had some of the kind of basic niceties of Rust included with it. So something like a string in Rust is a reference to memory that you allocated, and so it has a definite ownership lifetime. But something like an integer can just be copied around shallowly wherever you want. So the language just lets you kind of use it and implicitly copy it everywhere as much as you want. And I kind of tied this back in LabVIEW to the idea of forked wires. So a forked wire, I said, it's the same thing as a copy, and a wire can only be forked if the thing that's on the wire is safe to be copied at that point. So things that are implicitly copyable and references that are read-only, those are kind of the basic categories of things that Rust lets you just shallow copy. So I went on for about 2 years like this, and I was trying out some other kind of interesting ideas, like what if we could do more with our loop structures, like have objects that represent iterators, and what if we could have things like an option type or a result type like Rust has, whereas a union type between like a real value and an error value. What if we could just have that in the language, and we could have syntax that automatically destructures and handles the errors in different cases for you? And I think there were some neat ideas that came out of that. It was obviously only ever a one-man sort of project, and so that kind of limited the momentum it was able to get. But I think there are definitely some ideas that could be taken from that and apply to other projects.
Did any of those ideas ever get salvaged and put into like regular LabVIEW? Because I know when NXG went away, they tried to copy some of the ideas from NXG over.
Not that I know of. The reason why Rebar was like fundamentally a different language as opposed to just like an add-on or extension of LabVIEW was that I felt like the changes that you had to make in the type system and the compiler and the semantic analysis were so fundamental that like trying to sort of layer those on top of an existing established language and its rules would be difficult, if not impossible. So to my knowledge, they never really adopted anything like that into classic G.
Okay. So as you were describing some of the things about Rust, and I've played with it a very tiny bit, like part of the thing I like about it is it doesn't let you do dumb things, right? Like it won't let you go off the end of arrays and things like that. Mm-hmm. But I feel like some of that stuff was kind of already built into LabVIEW in the sense that like if you go off the end of an array in LabVIEW, like it doesn't warn you, but it does some somewhat sensible default behavior. Mm-hmm. As opposed to like C or something where it just returns random chunks of memory and you're like, eh.
Yeah, and part of that comes down to sort of like the decisions and the trade-offs that a language makes, right? So when you're talking about like a systems programming, the idea is that you want to give the programmer as much power and low-level control over things like performance and memory allocation and timing predictability as possible. So in C and C++, for instance, you have default manual memory allocation. You have to tell the language when you want to allocate and deallocate something, and otherwise it's just doing sort of like implicit stack allocation. Whereas in more managed languages like Python or Java or C++ or LabVIEW to a large extent, the memory is all sort of handled for you behind the scenes. You create a value and it's just there, and the language gives it to you, and then it decides later when to clean it up if you're not using it anymore. Some languages, they call that garbage collection. LabVIEW, it's not, to my knowledge, it's not really the same kind of garbage collection as a lot of other sort of mainstream languages that use that, but it's kind of the same idea. It's like automatic memory management. And that's nice for the programmer. It's very fast and simple to work in, but it can have, it definitely has implications for when you're trying to tune and improve the performance of your code. And what Rust tries to do is give you, to a large extent possible, the best of both worlds. It gives you the, sort of low-level fine-grained control over when things, are allocated, but it also provides nice ways of just making sure that like the right thing kind of happens automatically. And so, Rebar was also an attempt to say, okay, if we can use these rules that Rust sets up, from the get-go to provide these sort of nicer automatic defaults and provide sort of more, performance-oriented control, what does that give us? What advantages does it give us over LabVIEW?
Yeah, that's really interesting. Yeah, the one thing you had mentioned too was concurrency. Mm-hmm. And Rust has some protections in that way, right? Whereas like LabVIEW, I don't think does as much. Well, would that be an accurate statement?
I mean, I think so. So LabVIEW is fundamentally a concurrent language, right? Like that's sort of one of the big advantages of the data flow model is like you can lay everything out to say, like, instead of this is the order in which things should happen, this is the things that depend on each other.
Mm-hmm.
And then the compiler is free to say, okay, well, if these things don't depend on each other, I can run them in parallel. And under the hood, that kind of concurrency requires the compiler to know, okay, the memory that this thing is using and the memory that this thing is using, are they ever going to get overwritten at the same time? Or is can one use the other, or can they occupy the same place? Or are these two things using the same reference to an object? And if so, if they're running concurrently, do usages of that object have to be locked implicitly every time you do something? That's something that happens with referendums, for instance. And so, yeah, LabVIEW is, it's not that it's not possible to, create race conditions, but, a lot of the things that would sort of naturally arise, a lot of the concurrency problems that would naturally arise from letting you just do a lot of things in parallel are solved for you. In kind of a similar way to what Rust provides. So for instance, so basic things like, okay, you have, when you're talking about a value and whether you're just reading from it or writing to it, writers to the value need to be made sequential and have exclusive access, whereas readers can all be happening in parallel. The LabVIEW compiler makes those same kinds of distinctions under the hood. So it looks at whether you're if you have, say, an array value coming out of wire and going to lots of different places, it looks at whether you're just reading from it or writing to it, and it can make decisions about when that value needs to be copied versus just reused based on how you're doing that. But the difference is that LabVIEW doesn't impose any restrictions on how you're allowed to use it. It'll show you things like, I think there's a mode you can turn on where you see dots if a value gets copied based on how you're using it. It'll show you when the things you've done have resulted in copies, and so you can kind of play these games where you try to rearrange things so that stuff doesn't get copied. Whereas what Rust does is it says, okay, you have to follow these rules. You have to be explicit about when you want to copy things, and otherwise it's copying is not allowed, or something like that. But the result is that very explicitly and upfront when you're doing something that might potentially be expensive.
Okay. Yeah, that's definitely a different philosophy, right? It's more intentional than LabVIEW. Yeah.
Yeah.
Interesting stuff. Are you aware of the stuff that Jim is doing?
Yeah, I'm aware of some of it.
Okay. Yeah. Is any of it parallel to some of the stuff you were doing, or related at all, or is it completely different?
So Jim and I talked about, I think one of the things that his project involves is transpiling his abstract G language, which is similar to LabVIEW, to Rust, so that what you're running is ultimately code that's gone through the Rust compiler. And so we had talked, some about, what were the similarities between the sort of analysis that you do on a LabVIEW graph to train with Rust, and the analysis you do to check and compile and turn into machine code or rebar diagram. And there's a lot of common problems. Like, for instance, how do you take a node or a diagram that has nodes that run asynchronously? So doing file operations, network calls, things that might block the thread for a long time. And how do you break that diagram up into different chunks that can be scheduled and aren't blocking each other, so get the best use out of concurrency? It's the same, the same sort of shape of problem occurs when you have a data flow diagram, sort of regardless of the rules of the underlying type system or language. So yeah, we talked about that, and I think it's an interesting project, certainly, for a lot of reasons other than just the Rust transpiling. But it's certainly a fun idea to try to think about one language and then figure out how to express it in terms of another language.
Yeah, it's a very interesting project. I'll be interested in seeing where that goes.
Yep.
So, yeah.
Mark your calendars for the GLA Summit, March 25th and 26th, 2024. This is an all-virtual 24-hour conference that features a variety of presentations accessible to beginner and expert LabVIEW users. The best part? It's free. Don't miss out on this opportunity to network with LabVIEW engineers around the world. To learn more, go to glasummit.org.
So rebar now, is it just completely gone? Like it's just over?
I mean, the code's still up there on GitHub, but yeah, it was built as a plugin against a specific version of a product that no longer ships. So
Yeah.
I think that's pretty much about as close to dead as you can get.
Yeah, and NI has no interest in like making the old NXG editor available or any of that code available, probably. Not that I've heard of. Yeah. Okay. So the other topic that you wanted to talk about that I think is actually really interesting was had to deal with DevOps and testing and process stuff. Yeah. So you want to, yeah, I'll just give you the floor and let you go.
Sure. I mean, I guess, the more that I experience and learn and sort of experiment with testing, the more I come to realize that, I wish I had learned some of these things a lot earlier in my career, or like in college or something, or when I was first, starting out with programming. Because like, I don't want to like, generalize for everybody, but think about like how a lot of people start programming, right? Like they have like a book or a tutorial for, C or Python or Java or something. And what's the first thing they write?
Hello world.
Exactly.
Yeah, you should write the test for Hello World, right? Is that the...
Well...
Is that... Are you a TDD person or no?
I am, and we can get into that. But I'm not going so far as to say that the very first thing you do as a programmer should be to write a test for Hello World. But think about what Hello World does, right? Like, it's teaching you a lot of things for the very first time all at once. It's like, okay, this is what kind of like the basic structure of a program in your language looks like. But also, this is the process for, turning that source program into something that you can run, and then running it and seeing what it did. And that very first, like, do something and see what it did, feedback loop, is a process that you're going to repeat tens or hundreds of thousands of times in your career, depending on how far you go with programming. And then you build on that to say afterwards, okay, let's keep learning, the more complicated aspects and features of the language, learn things like control flow and variables and function decomposition, and then maybe later object oriented programming and concurrency and all these other really complicated topics and data structures and algorithms and so forth. But all the while you're doing it, you're still doing some form of write code, compile it if necessary, and then run it, see what it did. And testing is a more evolved sort of step function higher version of that basic feedback loop, right? Because what it lets you do is not just have yourself in the loop of like, okay, I did a thing and then I saw what it did, and then I sort of evaluated what it did and asked like, okay, was that the right thing? Is it what I was expecting? But testing allows you to insert code into that process to say like, okay, I have these expectations ahead of time of what I think should happen. So let me encode those in the code too. And then I'll run the code and I'll have the other code check what the code did. And now the process of asking, did my stuff work, is that much faster.
Yeah. Because
it's no longer me, looking at it and thinking, okay, was that right? Or, how could this have been better? It's the machine, saying, is what the machine did correct? And that, I mean, that is an incomparable step higher level of power from what you first started doing, right? Because you can build on that, basic technique to say, okay, I can write tests that cover all the aspects of the code I'm writing, from the smallest, functions and expressions and basic expectations to, integrating the entire thing together and it's all just writing programs that test programs and evaluate the behavior of programs. And I think the earlier you realize that, the farther you will be able to go. Or the more you will be able to accelerate your own sort of process.
Well, I find an accelerator for learning. Like right now I'm trying to learn Python, and like one of the first things I did was like, how do I write a test? So that then I can like, as I'm writing code and I think I'm doing it right in Python, is there some gotcha or something that I'm missing, and my test immediately tells me that.
Mhm.
So I find it very useful for that.
Yeah, absolutely.
But the other thing that this whole talk spawned though is, right, you start with the hello world and you get that short feedback cycle of I write hello world, I press enter, it runs. And then TDD gives you like a slightly larger feedback cycle, right?
Mhm.
You're testing much larger pieces of code and it's more automated. But then I think CI/CD is even a step beyond that, in the sense that, the TDD stuff, you're verifying that it does what you think it does. When you do the CI/CD, it enables you to verify that it does what the customer wants it to do, right? Because you can deliver it to them really quickly and get that feedback loop, as opposed to, when I started, like the old thing was like you shipped like, every 6 months or a quarter or a year or some really long time frame, right? And you shipped like 10 different features, and it was really hard to debug stuff because, okay, we shipped 10 features, something broke. Well, which one of the 10 features broke something?
Right.
Yeah.
Well, and I mean, as you go, one of the things you start to notice is that, first of all, feedback cycles come in all sorts of different sizes, but also there are some things just have different feedback mechanisms, right? So like, if you're trying to decide whether what code does is correct, that's typically easier for a computer to test and verify. If you're trying to decide whether what it does is what the customer wanted, well, the customer kind of has to get into that process, into that.
Mm-hmm.
You can't decide that on your own. The computer doesn't know either. So, recognizing that difference, it's like, okay, how do I get the feedback I need? And is it something that, the computer can help me with? Is also part of, making things go faster. But, having a sort of facility with these like, different sizes, large and small, of feedback cycles means that you also can decide at what level you want to start, right? So with TDD, it's like, okay, I generally am starting from, I have this new thing that I want to make work in the context of what the system already does. And maybe it's a really big thing, and maybe I can only sort of write like a huge acceptance test for that, and it's not going to pass right away, or it's not going to pass for a long time. But then as I'm thinking about how to decompose that, I know that that's going to decompose into different parts, and those different parts each have their own sort of cycles of validation. Those can be smaller tests, and those I can write first or earlier. And you eventually, as you decompose things, you get to a state where you have something that you can test and implement right away, and that's sort of the most immediately valuable thing. Is what can you do right now and see working?
Yeah, I think that's where a lot of teams actually struggle, is that I think they try to take too big of steps. And I don't think we're very good at breaking stuff down into tiny steps. And we're also not very good at doing, like, in agile circles, they talk about like the horizontal slicing. Because I feel like LabVIEW programmers, we always want to do the horizontal slicing. We always want to, like, I've got this instrument, I want to write the driver for all the functions for this instrument, as opposed to saying, what's the base functionality, and can I get that, and can I get the GUI to exercise that to make sure that everything talks to each other? And I think it's a real shame, because the end user, if you spend all your time writing out the driver, they don't see anything change, and they don't, like it said, disconnect with the customer, right? Like that's the whole trope of like, oh, the programmer disappears and I don't know what the heck he's doing, right?
Right.
But if you're delivering those vertical slices, and they can see, okay, well, now I can set the voltage on the power supply. I might not be able to do anything else with it, but I can set it to a single value. That's good. That's like something useful. And maybe that helps them test something else out, or they can slowly start moving their process over from whatever they were doing before, or yeah.
Yeah. Well, and sort of the theory is that, if you sort of, keep going long enough with both styles, on the one hand, just doing sort of everything horizontally and building up layers to what you want, or on the other hand, doing vertical slices through what you need. In theory, if you do both of those long enough, then you wind up at the same place, right? But in practice, it never actually works out that way because things change, plans change. The thing that you thought you needed to build at the outset when you were planning all these layers turns out not to be the thing that you wanted.
Yeah. So I have a question for you. Earlier, you mentioned getting customer involvement in the feedback cycle. Have you ever played around? Because I know you do a lot of stuff outside LabVIEW. Do you ever play around with something called like Cucumber, or have you ever heard of it? Or BDD, like behavior driven development. So there's this program called Cucumber, and my understanding, I've never used it, but it lets the end users write tests in like more natural language. And then somehow there's some engine behind it that translates that into code and writes some kind of like unit or integration type test that you can run. Does that sound familiar?
I have heard of tools like that, yes. To me, it strikes me as something that's sort of a nice idea, but I'm sort of inherently suspicious of, what are called, low code tools or things that'll, allow a non-programmer or a non-coder to do things that are ultimately coding activities. Which is not to say that BDD is a bad idea, that Cucumber is a bad idea. But I mean, at the end of the day, when you're saying, I want to specify a test, that is on some level code in some kind of language. It may not be the same language that the developers are writing in, but it's something with a structure and rules and, sort of an order and rules of interpretation. And it can ultimately pass or fail. That's a coding activity. I don't know, what were you going to say about it?
No, I mean that was I was just curious to see if you've seen that and see it work. I mean, I'm kind of skeptical of, as you are, and I like the idea of getting the end users involved, and I do think they should have some idea in determining like what the pass fail criteria is, but actually writing the test I think is kind of hard for them because like they're not programmers. And honestly, just getting end users to like do any kind of testing is really hard. Like a lot of times, like people come to me with test machines like, hey, we need to make this upgrade. I'm like, great. How are we going to test that this thing actually works? And they just like, I don't know. And like, I haven't really found a good solution for that other than like, hey, if we've got two testers, let's run and piece through both machines and run one that passes and one that fails and verify that the reports look the same. And like, that's at least a good first step. It means we didn't break anything major.
Yeah.
But like, I don't have a better solution than that. And like, quite often you inherit this legacy code that has no test period. So how do you verify that you haven't broken anything?
Well, I mean, every testing process has to start with the idea of, what is broken and what is correct, right? Like you have to nail that down before you can come up with any kind of a testing plan, whether it's manual or automated. And if you're starting from, well, I have a UI or I have a thing that I can run and I want to see what it does, you can formulate your plan in terms of what you see it do, what you think it's supposed to do. If what you're looking at is the implementation of the thing, then you have maybe a different idea of, well, what are the possible things that this could do, and are they correct or not? But yeah, you have to start somewhere, and you have to start with a language and and terms that let you specify like what's the space of possible behaviors, which of them are correct, and that is just kind of an inherently hard problem, I think.
Yeah, well, the one problem I run into is sometimes like they don't even have the original requirements and nobody knows what the thing's supposed to do. I've run into those situations before. And like sometimes people get so set on, oh, I'm going to re-engineer the original requirements, but those may have changed, right? And like I think of it as like as designed versus as built. Like the design requirements were this, the way it was built was something different.
Yeah.
Which one's correct? And if people have been relying on the as built for so long, and you find a problem, is it a problem or is it, like in some cases, like I remember talking to Steve Watson. I've told this story a few times, probably even on here, but like they were testing something and he replaced the tester and everything failed. And they're like, this can't be right. And then he went back and showed them the numbers. And it's like, yeah, your old tester should have been failing all these too. Right. And in that case, it did matter.
Mhm.
So, but like sometimes like the behavior is like subtle and it doesn't really, it's something that maybe doesn't matter as much, like what color an indicator turns or something, or like some, way the graph looks, or I don't know. It's just interesting.
Yeah, I mean, the things that people come to expect from usage, like from the code that's actually out there in the wild being used, that they're not even aware of, like you said, subtle behaviors. Those are the hardest things to nail down and test, because you may have no idea why it's even behaving that way, or if it was ever intended.
Yeah. Well, people are also really good at coming up with workarounds, and they get very attached to their workarounds. Like, for example, I worked on this one program where, like, in order to start the system, they had to like go to this tab and click this button, then go to another tab and click another button, and go over here and verify this value. And luckily, they were pretty open to changing that and making it easier on themselves. But sometimes you change that, and people are like, I don't know what to do now. And I'm like, well, you don't have to do these 3 steps. You do this 1 step. They're like, yeah, but it's different.
Yeah.
Yeah, and people certainly don't like change. And I think part of it too is it depends on the organizations too, because some organizations like, you can't change that. We have our 300-page user manual. We'd have to rewrite it. And I'm like, go rewrite it. Like, I don't know, maybe I'm underestimating how complicated that is. I'm like, it's a Word document somewhere, change a few things and reissue it. But I don't know, maybe if you have like, 300 operators and all around the world, maybe that's a pain in the butt. I don't know. But I would think the answer would be to change it. But
Well, so this was something that we struggled with a lot when we were working on LabVIEW NXG. This notion of like, what kind of change are users willing to tolerate? Because I mean, LabVIEW NXG sort of evolved over time to become what we thought was going to be. Sorry, when I say we at NI, where I used to work, was going to be sort of the if not the replacement for, at least sort of like the better version of LabVIEW. And of course, LabVIEW was like a 30-year-old product by that time. It had a ton of users, and like you said, they all had a lot of expectations built up over a long time of how things worked. And
like something as simple as changing a keyboard shortcut. Like,
yes.
remember like some of the changes from like in the, I think like LabVIEW 20 to 21, they changed some of the wiring behavior or keyboard shortcut, and people were just like up in arms about it.
Yeah.
And from the developer's point of view, like the developer working on LabVIEW, it's probably a trivial thing. You're like, eh. But everybody else has their muscle memory and stuff, and they're just like, oh, it doesn't work.
Well, yeah, it can be trivial things like that, or it can be things that, like, from the developer's standpoint, like the change is like, you want to say it's objectively better. There is no sort of objective evaluation of that. It's like it should be obvious that it's better, right? I'm trying to think of an example, but like,
well, taking something from like requiring 10 clicks down to like 1 click, right?
Yeah.
Like moving some menu items around or something. Oh, there's one. What did they move to the, what was it, create constant? They moved it to the top of the list, so it's easy to right click on a wire and click create constant. And before it was like clean up wire or something, right? And you create constants presumably more than you clean up wires. Or I guess maybe that was the thought process.
Well, I mean, that's the thing you have to evaluate, right? It's like you have to watch users in the wild and see which are they actually doing
more of,
which one's easier for them.
Yeah. But then that also probably varies between persons. So the majority of people might do one more often, and one person might do the other one, and then they're going to be upset. And yeah.
And then the answer there is, okay, well, how do we make it configurable?
That is a good answer. Yeah.
And which changes do we sort of impose on people and force them to accept versus like, which do we allow them to have control over? And that's easier for the smaller things, like sort of tactical UI stuff, like, okay, which option is first? But a lot harder for the big structural changes, like, is the call library in there defined at the individual node level, or is this their entire other document over here that defines like the interface to it? Those sort of like big decisions that LabVIEW NXG was trying to introduce. I think that was, this is my speculation, but I think that was a big part of why it did not see the adoption that and I was expecting, was that the changes it was trying to make were, you know, too much for the established user base to swallow. Relative to, you know, sort of the perceived benefit that they were getting from the new and improved product.
I kind of look at the whole NXG thing as a case for refactoring over rewriting, because I think if you would have and I mean, I don't know the backside code base, so maybe it was a complete mess. Like that was the official thing that I'd heard through the grapevine from well, unofficial, I guess, through the grapevine from I was like, this code base is horrible. We have to, you know, it's no longer sustainable. We have to do something else. But when you're refactoring, you can still end up at a completely different place at the end. But if you give them several versions in between where you're just gradually changing things, then the level of change is less. Versus NXG was just this big step change, I think. And I think that threw a lot of people off and kind of hurt some of the adoption as well.
Yeah, I mean, I think they are kind of independent concerns to some extent. Like, you can, in my opinion, you can be extremely diligent about code reuse and refactoring and, like, you know, what are the sort of common parts of these two things that we can, you know, pull in and reuse. And you can still introduce enough changes that make people not want to use the new thing.
There's probably like this like middle ground, right? Like, I feel like if you just drastically changed everything and you told people this isn't even your LabVIEW and it's drastically different from what you know, and you just mentally prepare them for that, they're probably willing to accept it. And if you just gradually start changing things to get to where you want, they're probably willing to accept that gradual change. But there's like that middle valley where you make a bunch of changes, but you still kind of say, it's still LabVIEW, it's just different. And then there's too much change and people are just kind of resist it. I don't know if that makes sense or not, but.
I mean, yeah, there could be. I mean, one thing I can say is that there was, in fact, a lot of shared code between LabVIEW NXG and LabVIEW, particularly in sort of the runtime and compiler system.
I was going to say the compiler was pretty much the same, right? It was mostly the editor that did a lot of it, right? I mean, I'm sure there had to be some changes because they changed the way they did libraries and stuff, didn't they? Or
yes.
Some of that type of stuff, yeah.
Yes. So yeah, the execution system was, I mean, it was a branch. It was forked and sort of periodically integrated with the original runtime system and and parts of the compiler that targeted that. But yeah, it was shared and had, you know, very much the same sort of under the hood concepts. But you know, that was very separate from what the user saw. And there was a front end of the compiler that was, you know, entirely new. It was written in C# as opposed to C++. But yeah, that I think, with maybe some exceptions, I think that was not the thing that introduced the changes that, you know, I think people had the most trouble with.
So I have a question. There's a lot of people in the LabVIEW community who are calling for NI to open source LabVIEW. Is that a crazy idea? Is that because my biggest thought on that is like the overlap between, like, the Venn diagram between the people who use LabVIEW and the people who are capable of maintaining it is basically zero overlap, right? Like there's not, I mean, my understanding is LabVIEW itself is written in C or C#, right? Or C++ or something like that. And it's text-based, and the majority of LabVIEW programmers are not text-based. And so I just imagine there not being much overlap there.
Well, so my understanding is, you know, some parts of it are, and some parts of it are written in LabVIEW itself. And I think there's been sort of this tangent, you know, desire for more parts of LabVIEW to be written in LabVIEW itself, so that, like you say, the people who are familiar with LabVIEW and all the text-based languages can do at least more extension of, if not development on, the language. Because yes, I think you've got it basically right. Like I think, you know, open sourcing LabVIEW could be a good idea for, you know, lots of reasons, but it wouldn't necessarily be that there would suddenly be a huge community of people able to contribute to the LabVIEW code base itself, you know, with the skills and tools that they already have. But I mean, yeah, that's not, yeah, again, it's not to say that there aren't other advantages to open sourcing it. Like, you know, just being able to see how something works is, you know, valuable sort of for sort of pedagogical purposes, or, you know, just inspection, or like, I noticed this bug, maybe I want to go see, like, where's that coming from? And I mean, of course, there are a lot of other considerations around like, sort of IP protection and sort of corporate versus community interests in LabVIEW that are hugely relevant to the question of whether to open source it. So I don't have a strong opinion on taking like, whether it's a good idea to take something, that old and that established and open source it. I think that because the other thing is like, when you try to build a community around an open language, like, Rust is a very recent example of this. There's now the Rust Foundation, and Python is a slightly older example, right? That that still means there is still going to be a core of people making decisions about the language, right, and guiding it, and trying to safeguard sort of the interests of the larger community. That doesn't really change, based on whether the code is open source or not, or who can see it. And deciding what's going to change in the language, where it's going to go, and who has a stake in that is, I think, just as important of a question as, who has the license to the source code and who can see it.
Mm-hmm. Yeah, no, I mean, that's the other thing, right? Like if I were to open source it, like I don't think somebody would still have to govern it, and I would probably still want to say in that. And so there'd have to be some kind of governance organization. And I could also imagine too, like some of these, did Microsoft or somebody fund somebody at the Python Software Foundation? I know like big companies have funded some of these open source things to put developers there. So I could also see that too, particularly since, there's a bunch of legacy C and C# code or whatever in LabVIEW that like the community doesn't have the skills to deal with. Hiring somebody would be a good way to do that.
Yeah, totally. I mean, managing the growth of a language is a totally different skill set from either using it or sort of like developing it proper, right?
Mm-hmm. Yeah. So one of the other challenges I think in the LabVIEW community, and I think open sourcing may help that, is just the whole idea of adoption. And I've had this conversation with Nancy lately about how you've used Rust. So if I want to go use Rust, right, I can go to the Rust language page and there's a thing that says try it now, and I click on it and it opens up a terminal in my web browser and I can type in a few commands and hit enter and go, right? And I don't know if you've done like the Cyber Dojo or whatever. There's this website, Cyber Dojo, you type it in. It gives you a list of all these practice katas, which are basically just exercise. You click on one, you click on the language you want, and again, it pops up a window and you can start typing and you hit enter and it runs and it has tests and it shows you what's going on. And like LabVIEW, if I tell somebody, hey, go try LabVIEW, they got to go to NI, they got to give them their email, they got to create an account, they got to verify their email, they got to sign in, they got to navigate the page to find the correct version to download. They have to make sure they check the community box, they have to download it, they have to install it, then it runs up and it's got to go through the license manager, they got to log back into NI, right? And all this stuff. And it takes like an hour to get to the point where you can be like, here's your hello world, type it in.
It's a process.
Yeah.
I mean, yeah, I kind of like, I listened to the episode recently with Steve Watts. I don't know how well this is, but yeah, the idea of like a sort of a community, like open VM image where you can just like, you download an image and it's a VM ready to go. You can just start using LabVIEW. I mean, I think it's a great idea for a lot of reasons, but particularly for the ease of use and like getting to that first like usage, for someone who's never used it before. Because yes, I think that's where LabVIEW as a very like IDE centric language is kind of at a disadvantage with other tools where you can just write something that runs in WebAssembly or something.
Yeah. Well, I mean, Python, right? If you're running Mac or Linux, all you have to do is open a text file, write 2 lines, and you can run it.
Yeah.
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 It requires nothing. Because
the operating system.
Yeah. That is definitely a privilege. So, yeah, Steve's thing is interesting. See, here's something else I mentioned. So we think that's actually a good, like, we see that as a huge step forward because we're used to the old way that NI does it. But somebody coming from Rust or Python or one of these text-based languages, that's still untenable to them, which is you know what I mean? Like they still look at that like, I gotta download this 10 or 100 gig.
Yeah.
Yeah, or it's not 100, but
I basically have to host another computer
yeah.
on my computer to use this piece of software.
Something I was thinking, I mean, so two ideas that popped into my head. One just popped in right now. It would be interesting if you could figure out how to do like X forwarding or something in Docker and just have it as a Docker image and just say Docker pull run and it pops up a LabVIEW window. That would be cool.
Mm-hmm.
The other thing I was thinking of is, you know, if someone were and this, to host a website that basically had a back end that had these virtual machines sitting there and they could just, you know, you log in and it spins it up on demand and throws it up in a web browser and says, here. I think that the technology exists to do that. I mean, it has to, right? Because I mean, I go to like one of my VPS, you know, cloud hosting things, and you say fire up a server of this, and you know, 10, 15 minutes later, or however long later, it pops up in the browser running. So like that has to exist.
So did you ever hear of or were you exposed to LabVIEW Web UI Builder?
No, I was not. What was that?
So this was, I believe, the very first project or product to ever come out of what became the LabVIEW NXG. It was one of the first things I worked on. So back in 2009, 2010, when Microsoft had a product called Silverlight,
Okay.
which was essentially .NET hosted in the browser, there was an implementation of the early LabVIEW NXG editor that ran in the browser.
Wow.
And it looked pretty different from what was eventually released, but it had like the multi-tab editor, and it had functional diagram and panel editor, and you could run stuff. And I believe the selling point was that, so for one thing, when you compiled stuff, it would send your code to be compiled on some kind of cloud server. But the other thing, the reason it was called Web UI Builder was the front panels you built actually turned into like built packages of like Silverlight, XAML and .NET code that you could then host somewhere.
Okay, cool.
Like basically as your own like LabVIEW web page. And there's a lot of reasons why that that ultimately went nowhere and didn't work out. One of them, a big one, being that like Silverlight ultimately was killed in favor of HTML5.
Yep.
And to my knowledge, there's never been an HTML5 LabVIEW diagram editor. But that's not to say that there couldn't be.
Yeah.
It would be a lot of work to build one, but all of that is to say that like the idea that you would just be able to go to a website and immediately be able to use LabVIEW in your browser is not totally crazy.
Well, there is the thing that used to ship with CRIOs that people used a lot, and I forget what it's called, Web Publishing Toolkit or something, that basically it didn't put the editor in a browser, but you could take a VI and put the front panel of a VI in a browser. And that worked pretty well, but that also relied on Silverlight, and that's also dead.
Yeah.
Yeah. So
that's not coming back.
Yeah.
I still have a shirt that says I heart Silverlight. Shirt all the time.
Cool. All right, so I do have a question that I like to ask everybody, and that is, tell me about a time that you tried an experiment of some kind, and it didn't turn out the way that you thought it would, and what did you learn?
I can think of examples of things that were, things other people tried, it didn't work, and that I had to deal with.
Yeah, well, what lesson did you learn from that?
Well, so I think one lesson is sort of germane to the testing discussion that I learned, at some point was it is possible to overuse mocks in unit testing. And there's kind of like, I think I'd say there's sort of a, an art and a science to knowing, how much mocking to use or where it's appropriate to use. People will tell you that like the disadvantage of mocks is that they can sort of lock you into decisions about your API and make them hard to change. So they refactor them, and that's definitely true. When I switched to I switched to working on the Monarch project, which was the code conversion tool from LabVIEW to LabVIEW NXG. the existing code base had a lot of tests, but they were tests that tended to really use mocks in a way that was that was inappropriate. Like they would be mocking like the data structures that came out of the thing that parsed current gen code, or they would be mocking like one part of the code would talk to another part of the code, and there would be a mock in between the two where really you just kind of wanted to use an integration test. And so that was at least a learning experience of like, well, as I have to make changes here, and I have to sort of detangle all these expectations that have been set up by these tests that no longer, maybe they were valid at one point, but they no longer really hold. That was sort of like a learning by counter example of like, maybe don't use mocks in this way.
Or would it be too, maybe test at like a higher level too, right? Because like if you test it too low a level, you're testing the implementation details more, right? You want to kind of test the general functionality.
Yeah, and I think where I've landed now is that like the place where you can best use mocks is as sort of like an interface or in front of the things that you absolutely cannot control, right?
Mm-hmm.
Every program is going to have like, there's the core, that's the stuff that you own, you control, and you develop. And then there's like a shell surrounding it that's like how you talk to everything else.
Yep. Like databases, web APIs, files, stuff like that. Yep.
Yeah. Anything that's like provided to you. Those things, maybe not always, but those are the things that are like the most useful to mock in my experience. And if you're anytime you're using a mock, you're effectively saying, this is something that I expect not to change, or whose behavior I can sort of pre-specify because it's not going to change. And if that's not coupled with an expectation that that the production like version of that is outside my control or is coming from somewhere else, then you're potentially setting yourself up for a situation where you're going to make change more difficult for yourself than it needs to be.
Yeah, no, I agree. Yeah, it is a delicate line writing tests, right? Because if you test absolutely every single line of code, well, then you can't change any of the lines of code, right? The whole point of the tests, in my mind, is to give you the safety net so you can make changes.
Yes, absolutely.
Yeah,
that is the value we give from tests.
Very cool. It's been a great conversation. Thank you very much, Ben.
Yeah, absolutely.
Yeah. All right. Thank you. That's it for today's episode of the LabVIEW Experiment. Thanks for listening. If you have any comments or questions, head over to thelabviewexperiment.com and drop me a note. And don't forget to subscribe to the podcast and follow us on Twitter and Instagram @TheLVExperiment.